In 7.4, in the Construct the Understanding, they want you to prove tan squared plus 1 equals secant squared and 1 plus cotangent squared equals cosecant squared. If you look up on the wall over here, I've got those written down here. They're on your formula sheet as well. In other words, you will be allowed to use these ideas moving forward in any proof that you have. Now, these ideas are connected to the idea, the big idea from chapter 6. Sine squared plus cos squared is always equal to 1. So if sine squared plus cos squared is always equal to 1, if I'm trying to prove tan squared theta plus 1 equals secant squared theta, and again, you'll never have to prove this one. It's on your formula sheet. This is allowed. Anytime you see tan squared plus 1, you can write secant squared instead. Anytime you see secant squared, you could choose to write tan squared plus 1. But for now, we're going to prove it. Okay? And we're going to prove it by changing things to sine and cos. If secant is 1 over cos, then secant squared is 1 over cos squared. If tan is sine over cos, then tan squared is sine squared over cos squared. And in mathematics with trig functions, when we square something, we put the squared between the sine and the theta so that you don't get confused with squaring the theta. If I put the squared after, a person can't tell, does he mean everything is squared or just the theta is squared? So technically, this means just the theta is squared. If I wanted everything to square, I'd have to add brackets. Mathematicians don't like writing brackets. It's like extra effort, so much time to write those blue brackets in. So they're like, hey, I've got an idea. If we want everything to be squared, why don't we just write the 2 in the middle, and that we'll decide that that means everything's squared. Then we don't have to write the brackets, and it'll save us so much time. Trust me, in these proofs, sometimes that would save you like 5 seconds. So much time. Okay. And I would have, so tan is sine squared over cos squared plus 1. What's the main strategy if you change things to sine over cos? Change it to sine over cos, then write both sides as a single fraction. This side's already a single fraction. This side's not. How do we add fractions? I would need a common denominator. So I'll multiply this by cos squared theta over cos squared theta. And then I'll get sine squared theta plus cos squared theta all over cos squared theta. I've got a single fraction on both sides, but they're not completely equal yet. Anybody see what I could do? I can't cancel. This would be tempting to cancel with these coses, but because there's a plus sign, this is all grouped together. I can change that to 1, because that's my big idea. Sine squared plus cos squared equals 1. And so this side just becomes 1 over cos squared. And now we've done our proof. So that means moving forward with your identities, you are now able to use this one with tan squared and secant squared, or this one with cotangent squared and cosecant squared. You're able to use those in your proofs. So for example, does anyone have their proof sheet out? Here, can I borrow yours? The sheet that I gave you the other day, number 17. Number 17 looks like this. 17. Oh, they're x's. Wow. So some people already came and said, what can I do with number 17? And you could do this one with the old strategies of changing to sine and cos. But now, since we have those new tools on our formula sheet, I'm going to say, whenever you see a sine squared and a 1, can you see that 1 minus sine squared is cos squared? That's using your big idea. Since sine squared plus cos squared equals 1, 1 minus sine squared would be cos squared. And now that we've learned that there's another big idea with tan squared, what's 1 plus tan squared? Secant squared. And so we had something, some of you were distributing, that's perfectly fine. You work through this one that way, that's perfectly fine. But if you notice these Pythagorean identities, and they're called Pythagorean identities because they're based on a squared plus b squared equals c squared. Because sine squared plus cos squared equals 1 was just using a right angle triangle on our unit circle. Well, now I just have cos squared and secant squared. I can change to 1 over cos squared. This is over 1. These are identical, so they simplify. I get 1. And my proof is done. So having our identities, our Pythagorean identities, and they're listed on your next page here. Sine squared plus cos squared equals 1. Tan squared plus 1 equals secant squared. Cotangent plus 1, cotangent squared plus 1 equals cosecant squared. And you can rearrange these. So if you can move something over, okay, they will allow you to do one mental math thing in your head on an exam for a proof. So if you know sine squared plus cos squared equals 1, you know that sine squared is 1 minus cos squared, and cos squared is 1 minus sine squared. So if you have 1 minus sine squared, you could change it to cos squared right away without penalty. If you do too much in your head and say, oh yeah, it works, then they, like, usually anything more than one step, they say you need to show your work. Happened one year on an exam. The exam had a nice, hard identity. The student looked at it and said, this is what they wrote on their exam. Ladies and gentlemen, it is obvious that blah, 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 blah equals blah, 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 blah. No work needs to be shown. The proof is done. They got 0, but we all laughed when we had to mark it. You can't skip 18 steps and just say, yeah, it works, good. You have to show your work. But you are allowed, if sine squared equals cos squared equals 1, you're allowed to do one step in your head. So if you had 1 minus sine squared, they'll allow you to change it to cos squared. If you had right? If you move the 1 over to the other side, can you see that tan squared would equal secant squared minus 1? If you had a secant squared minus 1, you could change it to tan squared, no penalty. That's just a simple mental math, one side to the other. Or you could move the tan squared over to the other side and get secant squared minus tan squared equals 1. If you did, oh, I'm going to move the 1 to this side and the secant to this side, they would say, show some work, because you did two things. Even though you probably can see that in your head, that tan squared minus secant squared is negative 1, they might want to say, can you show a little bit of that first? And finally, oh man, cotangent and cosecant, those ones could be rearranged once as well. Perfect. So let's do one example from here. Again, take out your scrap paper and try to prove these. One of the things that you're going to develop as you do more and more proofs is you're going to look at the question to see what strategy should I use. Okay, I look on the left side, I've got cotangent and tan. The left side would be pretty easy to change everything to tan, and I notice some of you did that. I look at my right side though, and my right side doesn't change to tan. My right side I can change to sine and cos. So knowing that, right away from the beginning, I might make the decision, I'll do that strategy where I change everything to sine and cos. Cotangent is cos theta over sine theta. Tangent is sine theta over cos theta. Cosecant is 1 over sine theta. Secant is 1 over cos theta. Change everything to sine and cos, and then step 2 of that strategy is write both sides as a single fraction. Well, the right-hand side, what's our rule for multiplying fractions? Multiply your numerators. 1 times 1 is 1. Multiply your denominators. We will get 1 over sine theta cos theta. Single fraction. Done. The left-hand side, I'm adding 2 fractions. How do I add fractions? I need a common denominator. So I will multiply the first one by cos theta over cos theta, the second one by sine theta and sine theta. That gets a common denominator of sine theta cos theta. And I can add my top. I will get cos times cos, which is cos squared theta, plus sine times sine, sine squared theta. So now I have got a single fraction on the left-hand side. But we're not done yet. In the past, when we did that, they turned out to be equal. But right now, on the one side, I have 1 over sine theta cos theta. On the other side, I have sine squared plus cos squared theta over sine theta cos theta. Is there anything I can do? Cos squared plus sine squared, that's a big idea. That's equal to 1. So we can change that to 1. And what do you know? Our proof is done. So again, the strategy of changing to sine and cos and getting a single fraction. In this case, I looked at my beginning question. Even though the left-hand side I could change nicely to tan, the right-hand side didn't change nicely to tan. That's why I made that decision. For the second one, a different decision is going to be made. Okay? Of my big ideas, sine squared plus cos squared equals 1. One of the new ones that we have is that there's a relationship between cotangent squared and cosecant squared. So when I look at this question, I notice that I've got cotangent, I've got a cosecant squared. What is cosecant squared equal to? Cotangent squared plus 1. So for this question, I can change the cosecant squared to cotangent squared plus 1. Now my right-hand side only has cotangent. This probably is going to be helpful. I can take this cotangent out in front and distribute it. That would give me cotangent cubed plus cotangent theta. And then I have minus cotangent theta. Oh, this works out really nicely. What's cotangent theta minus cotangent theta? Nothing. And we get cotangent cubed theta. Our left side is equal to our right side. So in this question, I decided not to change things to cos and sine. It could have worked. It would work. It takes about 3/4 of a page at least, but it's not wrong. But I noticed, hey, there's a relationship between cosecant squared and cotangent. So I could change the right-hand side so it only has cotangent. The left-hand side only has cotangent. That seems to make sense. Okay, so you have more proofs on that sheet when you take home. The questions from this one are 3, 5, 6 II, 7 II, 9 II. Ay, ay, ay.